Okay, so so far we've defined this notion of pack learnability, which is basically telling us how small can we make the estimation error for a given hypothesis class. Right now, we've said that we fix a particular hypothesis class, and our goal is to make sure that the estimation error is small. Once you fix the hypothesis class, you have no more control over changing the approximation error. That quantity is fixed. But the best you can hope for is ensure that the estimation error is arbitrarily small. All right. But then how do we decide whether a particular hypothesis class is pack learnable or not? In other words, if you want something to be pack learnable, it means that as you increase the number of samples, you can this epsilon and delta that you can achieve becomes smaller and smaller. Right. So asymptotically, you want as n becomes large, you want the probability that the output of your learning algorithm achieves a generalization error that is within an epsilon of the optimal predictor within your hypothesis class, and this happens with probability at least 1 minus delta, and epsilon and delta both go to 0 as n tends to infinity. Hopefully you want this to happen. And we've seen a couple of things so far. One is that if you have a finite hypothesis class, then the finite hypothesis class is pack learnable. And just because a hypothesis class is infinite does not necessarily mean that it is pack learnable or not. Certainly there are hypothesis classes which are not pack learnable. If you take the space of all possible functions from, let's say, an infinite alphabet to 0, 1, then the no free lunch theorem basically tells us that it is impossible to do pack learning on this particular hypothesis class. But those are two extremes, one where you have only finitely many functions, the other where you allow all possible functions. And what we are interested in is typically somewhere in between, some reasonably interesting class of functions. And what we've seen so far is that we don't have a complete answer yet. We've seen that if this hypothesis class satisfies the uniform convergence property, then it is pack learnable. But and moreover, ERM is a good learner, right? So it is not just that this class is pack learnable. We also have an algorithm that allows us to achieve an arbitrarily small epsilon and delta error. But then how do I decide? But the uniform convergence property is some property, but it is not something that you can easily verify. Somebody gives you an arbitrary hypothesis class. How do you decide whether this is indeed a Glivenko-Cantelli class or not? So for that, towards that, I defined this notion called the VC dimension. And this is very specific, as I said, this is very specific for binary classification problems with the 0-1 loss. And in this case, so the VC dimension, we'll see that the VC dimension characterizes pack learnability. And what is the VC dimension? So the VC dimension is based on this notion of shattering. So given a class, a particular hypothesis class, we say that the hypothesis class shatters a finite subset of m elements if when you apply these functions on all of these m elements, you can essentially generate all possible 2 to the m configurations, all possible 2 to the m labelings of these m points. All right. And the VC dimension is the size of the largest subset of your domain that can be shattered by this particular hypothesis class. All right. And I mean, intuitively, VC dimension is a notion of complexity of this hypothesis class. If the hypothesis class is very rich, then you can imagine that the VC dimension would be correspondingly large because you would be able to shatter more points. For example, if you look at the space of all possible functions from the domain to 0, 1, then clearly no matter how you choose, you pick any m points for any m, since you have all possible functions within your hypothesis class, you can generate all possible labelings of these m points. All right. So clearly the VC dimension of this particular class is infinite, because you take any set of any size m, this will always be shattered. because your hypothesis class contains all possible functions from the domain to 0, 1. All right. So that's one intuition behind the VC dimension. We'll see a little bit more about the intuition a little later.
What does labeling of endpoints mean?
So basically it is just this, right? So the labeling is h of x1, h of x2 up to h of xm. For a particular h, for a particular predictor, you get one set of labelings.
So it's only either 0 or 1?
It is either 0 or 1, yes. The labelings here are only 0 or 1, nothing else, positive or negative. All right. So for example, if you have 2 points and let's say 3 functions, then the all possible labelings are h1 of x1, h1 of x2. The other labeling is h2 of x1, h2 of x2. The third labeling would be h3 of x1 and h3 of x2. That's all. All right. So that's the definition of the VC dimension, and we were looking at a couple of examples. One particular example was the class of threshold functions, and if you take a subset of size 1, then you can generate 2 possible labelings. All right. So you take any function which has a threshold to the left of x1, then x1 would be labeled 0. If you take any threshold function that is to the right of x1, then this would be labeled 1. So this point is shattered by the hypothesis class H. But if you take any 2 points, 2 distinct points x1, x2, then what are the possible labelings that we can generate? You can generate the labeling 0, 0 by taking any threshold which is to the left of x1. You can generate 1, 1 by taking any threshold to the right of x2. So these are both labeled 1 and 1. You can generate 0, 1 by taking any threshold in between x1 and x2. But you can never generate the labeling 1, 0. Right? And therefore, the VC, this point, there exists at least one singleton that is shattered by the hypothesis class. But no matter how you choose these 2 points, you will never be able to shatter them. You will never be able to shatter 2 points. Therefore, the VC dimension is equal to 1 because the size of the largest shattered set is equal to 1. All right. Similarly, you can consider extensions such as, let's say you have 2 different thresholds, or you could take something which is the indicator of a union of k intervals. All right. So those are simple examples that you can work out. So let's consider maybe something a little more interesting. Let's take the set of all hyperplanes in R2. Right? Or in other words, linear classifiers in R2. Now, in general, it's easier to prove a lower bound to the VC dimension than it is to prove an upper bound on the VC dimension. To prove a lower bound, to say that the VC dimension is at least something, you just need to find whatever k points and show that this is shattered by your hypothesis class. On the other hand, to prove an upper bound, you have to show that no matter how you choose k points, you will never be able to shatter them, which in general is harder. All right. In the examples that we saw earlier, it was kind of more intuitive, but as you look at more complicated examples, it becomes more difficult. All right. So let's take linear classifiers in R2. We'll sort of see a proof via pictures. So let's take 1 point. All right. So clearly you can get 2 possible labeling. So what does a linear classifier look like? You take any line which may or may not pass through the origin. One side of this particular line or hyperplane is labeled say 0, and the other side is going to be labeled 1. All right. And for the same line, you can alternate between which side gets labeled 0 and which side gets labeled 1. More formally, or mathematically speaking, a linear classifier is basically set of all h of x, which can be written as indicator function of A transpose x greater than or equal to B for A in this case R2, but you could also consider linear classifiers over RD and B in R. Right? And so suppose I give you one such A comma B, which labels one side +1 and the other side 0, then how do you switch the labelings? When I say how do you switch labelings, how do you switch labelings by changing A comma B?
Inequality, changing the inequality.
So I'm not allowing you to change the inequality, I'm allowing you to change A comma B. So how do you switch the inequality by changing A comma B? Taking?
Instead of A, we have 1 by A.
1 by A? No. Minus A minus B. Right? That's it. You just flip the signs. Right? And the labeling gets switched. Right? Okay, so now suppose that I have one point, say x1, x2, that's the point that is given to you. How would you generate both possible labelings? I know that pictorially you can do it, you just draw a line and then you label one side 0, the other side 1. But how would you, let's try to do this a little more formally. How do you go about choosing a hyperplane? Which one? So x1, so I want to show that x1, x2, this particular point x is shattered by h. Correct. So how do you choose A? Let's do it a little more formally. Take any A, it doesn't matter. In particular, let's pick an A that does not pass through x1 comma x2. All right. Let's yeah. In fact, any A is okay, and pick any A comma B such that A transpose x is not equal to B. Then it must mean that either A transpose x is greater than B or A transpose x is less than B. Right? Or A transpose x is less than B. Right? In case 1, it means that you've already got one particular labeling. In this case, this h of x is 1. Right? And if I take minus A transpose x, this is less than minus B. So the corresponding h prime of x is equal to 0. Right? Similarly, in the other case, if A transpose x is strictly less than B, then h of x is 0 and minus A transpose x is greater than minus B. So the corresponding predictor assigns the label 0 to this point. So I found two predictors from my hypothesis class, one predictor which assigns +1, the other which assigns 0. So take any singleton, this is shattered by the hypothesis class.
The hyperplane has to be straight in the end. It can't be any other curve. It has to
No,
be
no,
straight
it has to be a straight line, yes, but not necessarily passing through the origin. Okay, so this is one point. What about 2 points? Let's say x1. Yes, question? So if you take, so suppose h bar of x is equal to h bar of x is simply indicator minus A transpose x greater than or equal to minus b. What is this equal to? Huh. So these are two different cases. If A transpose x were less than b, right, to begin with, then minus A transpose x would be greater than minus b. Okay, you're right. This was a mistake. This should be 1. Correct. So essentially I can generate, all I want to claim is that I can generate both possible labelings, +1 and 0. Okay, so now let's take 2 points. Is it possible to generate all possible labelings?
It is just derivative, right? H dash of x.
No. H dash is something else, a different function. So more precisely, h prime is this function. It has nothing to do with the derivative. Okay, so now let's suppose I have 2 points. Any 2 points, x1 and x2. Can I generate all possible labelings? I can. Again, if I take both points to be on one side of this hyperplane, I can generate 0, 0 or 1, 1. If I take the hyperplane to pass to sort of split, to partition x1 and x2, then I can generate 1, 0 or 0, 1. So all 4 combinations can be generated. So H shatters x2. What about x3? Can every 3 points be shattered? Why not? Is that necessarily true? Yeah? Correct. It can't be shattered. Huh. So firstly, what do we need to prove to get a bound on the VC dimension? Do we need to show that every 3 points are shattered? We don't, right? We just need to find 3 points that can be shattered to prove that the VC dimension is at least 3. Correct? So let's take these 3 points that are not collinear. Now, can these be shattered? Right? So indeed they can be. So to generate 0, 0, 0 and 1, 1, 1, you take the hyperplane to be on one side. Then you can, if I take a hyperplane that looks like this, I can generate 0, 0, 1 and 1, 1, 0. using a hyperplane like this, I can generate 1, 0, 1 and 0, 1, 0. And using a hyperplane that looks like this, I can generate 1, 0, 0 and 0, 1, 1. So all possible labelings can be generated. So in fact, this particular x3 can be shattered by h. Not every 3 points can be shattered by h. That's important to note. I'm sorry? It's going to be difficult to get a really closed form expression, but given any 3 points, you can pick 3 points, 3 explicit points, and then get expressions for the hyperplanes. Right? Does that? So, for example, let's take the 3 points to be let's take one of the points to be 0, 0, the other point to be, let's say, 1, 0, and the third point to be 0, 1. Zero, 0, 1, 0, 0, 1. Then potentially one hyperplane, one choice of the hyperplane would be the following. So this would be one hyperplane that generates 2 possible labelings. The second hyperplane that generates 2 possible labelings would be this. The third hyperplane could be, say, something like this, and I leave it to you to generate explicit constants a1, a2, and b corresponding to each of these hyperplanes. Right? And the third would be, let's say, something that look like this. Right? So you can use intuition to guess what the 3 points should be and what the corresponding labelings should be, or the predictors should be. But you can also get closed form expressions for all of these. For a general set of 3 points, it's a little harder, but again, to show that to get a lower bound on the VC dimension, you can take any 3 explicit points. Now, what about 4 points? Is it possible to shatter 4 points? Yes? No? How many say yes? It's okay, it's a guess, it doesn't matter. Okay, how many say no? Okay, people who say yes, can you give a shattering set? Can you guess?
Let's say we take a straight line.
Okay.
It doesn't include any of the, let's say, n points, 4 points in this example.
Can you give me 4 points?
Yeah, then you can always shift that line to include 1 point, then shift that line to include 2.
Okay, so let me take, say, these 4 points, right?
We can have a line that includes just 1 point.
We can have a line that includes just 1 point. So,
Keep on shifting that.
so how many configurations can I generate with this? 2, right? 2 possible labelings. So 2, 2, 2, 2, right? How many possible labelings have I generated? 8, right? Now can I generate the remaining labelings? What next?
Line that is parallel, that doesn't.
Okay, let me perhaps write down. Let's take this. This is 1, 2, 3, 4, and I have 1 and 2, one above all of these 4 points. So now how many labelings have I generated? 14. So I'm still missing 2. All right. So is it possible to generate the following labeling? One, 1, 0, 0. Can I get a hyperplane that gives me this possible labeling? Using straight lines you can't, right? So this particular labeling can't be generated. Are we done? Does it mean that VC dimension is that every 4 points can't be shattered? Which one? I've only demonstrated this for these 4 points. I can't, right? Does it mean that I have done it for all possible configurations of 4 points? Yeah, we don't know, right? So that's why you need to sort of take all possible cases. So in this case, this is one case where the convex hull of x4 is basically a quadrilateral. All right. Now I can possibly generate all cases. So one where the convex hull is a triangle, and the other where the convex hull is just a straight line. All right. These are the only 3 cases that can possibly happen if you think about it, right? Because we are assuming that 4 points are distinct. So the convex hull can either be a straight line or a triangle or a quadrilateral. In case of a quadrilateral, at least we believe, we're fairly convinced that these points cannot be shattered. Right? So let's take the second case where the convex hull of x4 is a triangle. So essentially I have 3 points which are not collinear, and the 4th point lies within the convex hull. Right? Can this be shattered? Can you generate the following labeling? 1, 1, 1, 0. You can't, right? Basically, if the points along the edges or the vertices of the convex hull are labeled in a certain way, then every point in the interior should also have the same labeling. All right, and that essentially follows from the fact that if you take a linear classifier, then the regions which are labeled 0 and labeled 1 are both convex sets. They have to be convex. So this labeling is never possible. This cannot be generated. And the same thing happens even when the convex hull of x4 is a line. I have 4 points, all of which lie on the same straight line. Can I ever generate the labeling 1, 1, 0, 0? I can't. Right? Again, it boils down to the same property that If the extremities of the convex set has a particular labeling, then every point in the interior should also have the same labeling. Right. So no matter how I choose these 4 points, I'll never be able to shatter them. Therefore, the VC dimension of the class of hyperplane classifiers is equal to 3. In general, the VC dimension of hyperplane classifiers turns out to be equal to d plus 1. Again, this requires, I mean, it's harder to prove this using pictures for general D, but again, you can use results from convex analysis to prove the same thing. Essentially, it boils down to nothing more than just this. For D equal to 1, agreed. So D has to be greater than or equal to 2. Right. Sorry, even D equal to 1, it works, right? Because it's threshold, but I can label both sides. So I have both indicator x greater than or equal to A and also indicator x less than or equal to A. So it holds true even for D equal to 1. Any 2 points can be shattered, but no 3 points can be shattered. And yeah, the nice, anyway, let me not say anything more about this particular example, but basically the VC dimension is equal to D plus 1. Okay. And yeah, essentially the idea is very similar. In 3 points, if you take the linear classifier in 1 dimension is just indicator x greater than or equal to alpha. It consists of functions of the form indicator x greater than or equal to alpha and x less than or equal to alpha for all possible alpha. So H1 right, let's maybe just take one more example and stop at that. Take the set of all possible polynomials of all degrees and use that to define the classifier. So H is the set of all h of x, which can be written as indicator function of p of x greater than or equal to 0 for p of x being a polynomial. Right, of any possible degree. What do you think the VC dimension should be? Yeah. Okay, it's infinite. Why?
The way science is
In a straight line and
between any 2 points which are of opposite classes, we can pick another point and we can make the polynomial pass to that point.
yeah, root of that.
Sure. In this case, you basically assign a particular labeling. Let's say you want. Fine. So take any. Take any, let's say m, which is a positive integer, and pick any points x1 up to xm and corresponding labelings y1 up to ym. Let's say that say z1 to zm are such that zi is equal to one if yi is 1 and minus 1 if yi is equal to 0. Okay. Now given any xi zi, there exists a polynomial of degree, let's say m plus 1, such that zi is equal to p of xi for all I. Right? Given any m plus 1 points, there exists a polynomial that passes through this. There exists a polynomial of degree m plus 1 that passes through these m points. And the labeling that is generated by this polynomial classifier is exactly as we want. So for every possible labeling, I can find a polynomial that assigns this particular labeling. So all possible labelings can be generated, and therefore you can shatter this. Since this holds for every m, the VC dimension of this particular hypothesis class is infinite. Okay, so maybe one more example. Let's take a finite hypothesis class. Take any finite hypothesis class. What can you say about the VC dimension of this hypothesis class?
If it is full of polynomial functions, the highest degree plus 1.
It can be anything arbitrary, right? Can you, of course, you can't really say the value of the VC dimension, because H can be anything. It can be some weird looking hypothesis class, but can be at least derive an upper bound on the VC dimension. So if xm is shattered by H, how many distinct labelings should be produced by H restricted to m? 2 to the power m, right? Then should be equal to 2 to the power m. Again, this definition of shattering, nothing more, right? How many possible labelings can H generate? Yeah? Finite, but how many? size of H, right? There's no way that H can produce more than size of H distinct labelings, right? But the size of H when restricted to xm can only be less than or equal to the size of H, right? So which must mean that 2 to the power m or 2 to the power of the VC dimension should be less than or equal to the size of H. So the VC dimension is upper bounded by log of the cardinality of H to base 2. So clearly finite hypothesis classes have finite VC dimension, and here is an upper bound on the VC dimension. Can't be any larger than this. Why does there exist a polynomial of degree m plus 1 that passes through m points? Okay. If you've not seen this before, basically you can write this as a system of linear equations. So you want p of xi to be equal to zi, right? Equal to zi means that I should find some 1 plus alpha naught plus alpha 1 xi plus alpha 2 xi square plus alpha m xi power m should be equal to zi, correct? This can be written as an inner product between 1 xi square up to xi power m alpha naught alpha 1 alpha m equal to zi. Okay. So given m distinct points, I have 1 x1 square up to x1 power m, 1 x2 square up to x2 power m, so on 1 x3, so on up to x3 power m, alpha naught alpha 1 up to alpha m equal to z1 z2 up to zm. All right. Now this, so this is basically if there exists a polynomial that passes through these m points, then it means that I should be able to find a solution alpha naught to alpha m that satisfies this particular system of linear equations, which is possible as long as this matrix is full rank, right? This matrix has a special structure, that is each column is basically a 1 power higher than the column to the left, right? This is you take x1 through xm, so this should be xm up to xm, x1 through xm. This is this column raised to the 0, this is the column raised to 1, this is the same column raised to 2, and so on. This is what is called a van der Waals matrix. And you can prove that this is full rank as long as the xi's are all distinct. I'm sorry? This is a polynomial of degree m. Yeah, actually, I just needed degree m. Because degree m contains m plus 1 coefficients, so that's fine. All right. So anything greater than or equal to m is sufficient. Is that? I mean, it's not a full proof because I haven't proved that a van der Waals matrix has full rank, but it's sort of a fact. All right. This is a linear algebraic fact, so to speak. But anyway, the fact that you can express polynomial equations in a linear algebraic form is itself interesting in its own right. Okay. Any other questions? So we've seen a bunch of different examples of hypothesis classes, and in particular, finite hypothesis classes have finite VC dimension, and there are hypothesis classes that have infinite VC dimension, and there were also infinite hypothesis classes which have finite VC dimension. Okay, and so far I've claimed that if it has finite VC dimension, then it is pack learnable, agnostic pack learnable. We have not proved that yet, but does it mean that if the hypothesis class has infinite VC dimension, then it is necessarily not pack learnable? Let's go ahead and see why that should be the case. So here's a claim.
Does every
Yeah.
hypothesis class with finite number of parameters have finite?
No, right? As I said, I didn't prove this, but I think it's one of your homework questions that if you take, oh no, I have not assigned that homework yet, but so if you take this particular hypothesis class, h of x equal to indicator sine alpha x greater than or equal to 0, right? This has exactly one free parameter, alpha, and you can show that this hypothesis class has infinite VC dimension. Okay, so number of parameters is not necessarily a good measure of the VC dimension. So if h has infinite VC dimension, then h is not pack learnable. When I say it is not pack learnable, it means that you can't even learn the concept class h. If I take h to be the concept class, then I can't achieve arbitrarily small epsilon delta error for this concept class. And the proof is basically based on the no free lunch theorem. All right, so we'll have the following sub result. So let's say that is some set, or let me put the following way. Let's suppose you have a training set of size n and some set of size 2n is shattered by H. Okay, so you have n training samples, and there somehow exists a set of size 2n in your domain which is shattered by H. Then for any learner that outputs some particular Hs, it takes the training set as input and outputs some Hs, the probability that the generalization error achieved by Hs is greater than or equal to R of H star. In this case, I'm taking pack learnability of the concept class H. So this can be made equal to 0 plus 1/8 is at least 1 by 7. So with probability at least 1 by 7 bounded away from 0, the generalization error is lower bounded by some absolute constant. So no matter what I do, with these many samples, with n samples, it is not possible to achieve, no learner can achieve a smaller epsilon delta error than 1/8, 1/7. All right. And this is essentially just a direct consequence of the no free lunch theorem. Let's go back to see the statement of the no free lunch theorem. It says that if you have any learning algorithm on some alphabet x and the number of samples is less than the size of the domain divided by 2, right? And you're considering the hypothesis class of all possible functions from the domain to 0, 1. That's the setting of the no free lunch theorem. So here you're allowing all possible functions from x to 0, 1, and the number of samples is less than or equal to the size of the domain divided by 2. Then there exists some distribution. In fact, in this case, there just exists a distribution on x such that there is some function that achieves 0 error, 0 generalization error. So the ground truth is described by some particular function within this space of all possible functions from x to 0, 1, but no learner will be able to achieve an error which is less than 1/8, 1/7 if you don't have any more than n samples. Okay. Now you want to apply this to a case where the hypothesis class is not necessarily the set of all possible functions, it's some restricted class of functions, right? But we can still use this because the hypothesis class shatters xm. Right? So you look at the restriction hxm. So the hypothesis class restricted to hxm is precisely the class of all functions from xm to 0, 1, right? Or hx. Let me modify this slightly. Let me take 2n plus 1, 2n plus 1, 2n plus 1. All right. So this is since this set is shattered by the hypothesis class, h x 2n plus 1 is the class of all possible functions. So if I have fewer than 2n plus 1 divided by 2, which is n, which is strictly less than or less than or equal to n by 2 samples, less than or equal to n samples, then the no free lunch theorem basically tells me that there exists a function within this hypothesis class that achieves zero error. So the ground truth is described by some function within this hypothesis class. Let us call that h star. This h star achieves generalization error 0, but no learner is going to be able to achieve less than 1/8, 1/7 error. Right? So the no freelance theorem says that even if I restrict myself to just this hypothesis class, to just learning the labelings for x 2n plus 1, I can't do it. I can't do that reliably. So if I can't do it on this restricted set, then obviously I can't do it for all of x. So over the more general class of functions, the error can only be larger. Because I can't even learn a restriction. I can't even learn h x 2n plus 1. So obviously I can't learn h. Alright. And since this is true, so therefore if the VC dimension is some particular d, you need at least d by 2 samples in order to be able to achieve a small epsilon delta error. If you have any fewer than d by 2 samples, then there's really no hope. So the minimum number of samples you require is at least d by 2. We don't know how much more than d by 2 you require, but any less than d by 2 is no good. All right. In particular, if the hypothesis class has infinite VC dimension, then it doesn't matter. Any finite number of samples is insufficient to achieve an arbitrarily small epsilon delta error. All right. So if h has infinite VC dimension, then h is not pack learnable. And the intuition behind the result of this particular lemma is the following. So you see that you take whatever, let's say roughly 2n points, and h, when restricted to these 2n points, is all possible functions. Right? So you can generate all possible labelings for these 2n plus 1 points. Now if you see a sample, any random sample of which contains only n points, then it is impossible to say what will happen to the labelings of the other n plus 1 points, because all possible labelings are equally possible. Right? So you've seen only half the number of points. For the other half points, there exist functions which generate all possible labelings for the remaining points that you have not seen, because you only observe half the number of points. Right? Because n is whatever, less than half of 2n plus 1. So this means that it's not possible to learn the hypothesis class well enough. And the no free lunch theorem just quantifies how badly you will do. All right, does that make sense? Any questions? Okay, so now we've seen that if the hypothesis class has infinite VC dimension, then h is not pack learnable. We still haven't seen that if h has finite VC dimension, that it is pack learnable. I've not proved it, although I've stated it as a fact. All right. So we'll see a more general result that ties together a lot of different things for pack learning in the specific context of binary classification with the 0-1 loss. So we'll call this the fundamental theorem of pack learning. So consider a problem where H is a hypothesis class over some xy, where you are looking at binary classification and L is the 0-1 loss. Then the following statements are equivalent. So which means that if one of these statements is true, then the remaining must be true. If one of them does not hold, then none of the others can hold. The first point is that H has the uniform convergence property. So the empirical risk, so with a finite number of samples, all of the empirical risks corresponding to all of the predictors within your hypothesis class are epsilon close to the corresponding generalization errors, and this happens with probability at least 1 minus delta. Right. The second is ERM is an agnostic packed learner for H. Right. When I say ERM, note that the ERM is not necessarily unique, because ERM says you choose that function, you choose that predictor for which the empirical risk is minimized. Now there could be ties, right? There could be multiple predictors which achieve the minimum empirical risk, and you need a rule to distinguish which particular predictor you will choose. So based on how you break these ties, you can get different ERM rules. Okay, but nevertheless, the performance is still going to be the same. The claim is that you take any ERM rule, you still have the same property. Third property is H is agnostic pack learnable. The fourth is that H is pack learnable. When I say just pack learnable, it means that if I take H to be the concept class, then it's possible to do pack learning on this concept class H. The fifth is that whatever ERM is a pack learner. For H. The last is that H has finite VC dimension. Okay. We've seen a lot of this already. Like, we've covered most of it except perhaps for one point. Right. So if H has the uniform convergence property, then we've seen that ERM is an agnostic pack learner. Right, because all of the empirical risks are arbitrarily close to the generalization errors. We saw through that triangle inequality property that ERM can in fact achieve agnostic pack learning. So 1 implies 2 is something that we have already seen, and if ERM is an agnostic pack learner, then obviously H has to be agnostic pack learnable. That's straightforward because we have one learner. There could be other learners as well, but there exists at least one learner that achieves arbitrarily small epsilon delta error. So the class is agnostic pack learnable. Now if H is agnostic pack learnable, then it is obviously pack learnable because agnostic pack learning is more general than pack learning. So 3 implies 4. Now if ERM is a pack learner for H, then H is pack learnable. The reverse may or may not be true so far, right? So I have 1 implies 2 implies 3 implies 4, and I have 5 implies 4, right? And if ERM is a pack learner for H, then H has to have, in fact, if any of 1 through 5 is true, then the VC dimension must be finite, because if the VC dimension is infinite, then none of these can hold. All right. So 1 up to 5 must imply 6. Okay. So if I am able to show that 6 implies 5 and maybe 6 implies 1, then I'm done. Okay. So okay, also something else I should point out. I'm sorry? So yeah, of course 2 also implies 5, which is something that I will also use. 1 implies 2 implies 5 implies 4, right? Because if ERM is an agnostic pack learner for H, then ERM is a pack learner for H, and if H has the uniform convergence property, then ERM is an agnostic pack learner and therefore a pack learner for H, right? So if I am able to show that 6 implies 1, then the circle is complete, then they're all equivalent to each other. All right. So I only need to show that 6 implies 1. So if H has finite VC dimension, then it satisfies the uniform convergence property. Questions? So now the question is, how do we prove that if H has finite VC dimension, then H has the uniform convergence property? But we'll also try to do something beyond just that. If H has finite VC dimension, then can we also derive a bound on the sample complexity for uniform convergence? That is, if I want, recall what the uniform convergence property is. So the uniform convergence property is that for every epsilon and delta greater than 0, I should be able to find some NHUC such that the probability that I get an epsilon by 2 representative sample is at least 1 minus delta as long as the number of samples is greater than or equal to nh. So this quantity is what I call the sample complexity for uniform convergence. And my goal is to also bound the sample complexity of uniform convergence by the VC dimension. So in other words, if the VC dimension is large, then this NH will also be large, and if it is small, then this should also be small. All right. And for this, we'll use some of the concentration inequalities that we've seen previously. The idea is kind of similar to what we did, at a very high level. It's similar to what we did in the when we looked at finite hypothesis classes. But now I can't use that union bounding technique. That doesn't work anymore. Because if you recall what we did for finite hypothesis classes, we showed that we first derived an upper bound on the probability that the empirical risk deviates from the average risk by an amount epsilon. We saw that that is exponentially decaying in n, and then we took a union bound over all possible predictors within the hypothesis class to show that for all predictors you have uniform convergence. Right? We can't do that union bounding anymore, so we need a completely different approach. And in fact, what we will do is we look at what is the maximum deviation among all possible predictors within the class. So in other words, what is supremum over R of h minus Rs of h over all h in the hypothesis class. So one thing to note is that, let's say that you are using ERM, okay? If Rs of h is, you choose that h for which Rs of h is the minimum, right? So if it so happens that R of h is much smaller than Rs of h, it's okay, because your generalization error is anyway smaller than what you estimated. But you don't want it to be too large. And that's why we look at this particular quantity. If this quantity is small, then it means that the generalization error cannot exceed the empirical risk by too much. So if I choose the one with the least empirical risk, then hopefully the generalization error is also going to be sufficiently small. All right. In any case, we'll bound this maximum deviation, and if you recall, this showing that this particular quantity concentrates was one of the questions in your second exam. All right. So concentration is kind of, we get it almost for free with just a little bit of effort, just using McDermott's inequality. That's all that is required to prove that this quantity concentrates. The slightly more effort will be in finding the expected value of this particular quantity. In fact, that is what will take the bulk of the effort, to show that this is upper bounded by some function of the VC dimension. Okay. All right. So we'll continue with that in the next class. Maybe let's stop here.